and it is the negative binomial. Now, it is very closely related to, the geometric. So it's not a fixed number of attempts. Oh, I was doing these in blue, wasn't I? Not fixed n of attempts. In fact, x is the number of attempts. However, we have a fixed number of successes. So in fact, this is also sort of why it's called a negative binomial. It's the flip of the binomial. The binomial, we have a fixed number of attempts and we measure the number of successes. The negative binomial is we've got a fixed number of successes that I want to achieve, and x is the number of attempts required. And it's also like the big brother of the geometric. The geometric is saying, well, how many attempts until I get one success? Well, the negative binomial expands on it. So, well, what about we look at the number of attempts until I get 2 successes, 3 successes? So really, a geometric is just a negative binomial with r as 1. All right, it's just r as 1. It's kind of cool. So anyway, what else do we need to say about it? And basically, the xth success is the last one. And I'll try and talk to you about where this formula comes from as we go through this question. So part A is a great way to start on that. So we're taking 3 free throws. That's the thing, right? On each throw, the probability of scoring is 1 in 4, 0.25. Find the probability that the player scores for the 4th time on their 10th throw. So we know that it needs to be the 4th time. Now, this is a negative binomial, but we don't actually need to know about the negative binomial to figure R1 out here. So he's got 10 throws, right? And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. However, in these 9 throws, I need 3 successes. Why do I know it has to be 3 successes in the first 9 throws? It's because he's stopped. We stop at our 4th success on the 10th throw, so that needs to be a success. So we've got 3 successes in the first 9. Well, 3 successes in the first 9, basically the first 9 is a binomial n 0.25, and we want the probability that x is 3. So it's n choose 3 times 3 successes, 0.25 to the 3, times the 6 failures, and then we've got that success on the 10th attempt. All right, so we do need that choose function because these 3 successes in the first 9, that one can happen in a lot of ways, right? The 3 successes in the first 9 could be the first 3, could be the last 3, could be any random 3 in there, which is a binomial. That's where the binomial coefficient comes from. That is also NC3 to you and me. All right. So this is where this response comes from. I don't think the CG50 treats the negative binomial as its own thing. I don't think it's in here anywhere. No, it doesn't. So we're going to have to do it like grown-ups. Options, probability, so 9, choose 3 times 0.25. That's going to be to the power 4 in total, times 0.75 to the power of 6. So we should get 0.0584. Yes, so path, sorry, just to say what path is using. This is why I tend not to use this. There are two different ways to think about the negative binomial. X could either be the total number of attempts, or X could be the number, basically X can either be, in this case, 10, or I think the formula you have there is for n minus 1. So you're saying X is the number of attempts before you get that last success. Um, it's why, quite honestly, it's not that useful. Now, these two results here are quite interesting. These two results are quite interesting. Because what you can think of here is, if you want to stop on your fourth success, right? The other thing to think of is, well, just think of it as how many goes until the first success, second success, third success, fourth success, right? The number of throws in between each success is just geometric, right? So the number of throws, attempts between each success is just geometric, right? Let's just go to the first throw. That's a geometric. Right, cool. We count how many successes, how many attempts. Then we do another geometric to get to my second success, another geometric to get to my third success, another geometric to get to my fourth success. Well, in which case, the total expected value, if you want 4 successes, is 4 times the expected value for a geometric. And for variance, it's 4 times all the variances. Oh, did we have a bit of lag here? Are we back up? Hopefully we are. So these formulae here, you can just get them from the geometric distribution as well. Because all you're doing is you are adding up a whole bunch of geometric distributions. Now, part 2, on the other hand, exactly 4 times in the first 10 throws, well, that is now just a binomial. All right, so that is the difference, is we're going to do 10 throws no matter what. And we want the probability of 4 successes, and we can figure that one out. And same for part 3. We actually just want the probability here. Actually, let's use a different letter. That'll free us up a little bit later on. Fewer than 4 times in their first 4 throws. So fewer than 4 is a property that y is less than or equal to 4. Let's just get these probabilities out in one go. So exactly equal to 4. I could just go 4, 4. We're doing 10 goes. 0.146. Strictly less than 4 is less than or equal to 3. Mea culpa. That's on me. I assume when I look up at the chat, there'll be some clarifications in there for me. 0.7759. So Snuffler, the geometric, the whole point of the geometric is that you don't know how many throws it will take for a single success, right? But a key idea that you can use in probability is break a more complicated problem down into smaller problems. So if I want 4 successes, well, and we don't know how many attempts it'll take, you can count the attempts to get to the first success, which is a geometric. The number of attempts then to get to your second success is another geometric. The number of attempts to get to your third success is another geometric, and the number of attempts for your fourth success is another geometric. Is another way to think about it. And by and large, you're not going to use that, but it's useful for these expected values and variances. So the player wants to score 3 throws. Find the probability that he achieves this in 5 throws or less. All right, so here we want to get 3 successes. All right, so this is basically, let's use Z. Let's use Z. We haven't used Z yet. Z is a negative binomial. We want 3 successes. Probability of success is 0.25. We want the probability that Z is less than or equal to 5. Now, you might be thinking to yourself, but Nick, that's like so many to do. The calculator doesn't do this for us. Well, in fact, no, because there's only 3 probabilities. The strictest, smallest amount you could get is in 3 throws. Then it could take 4 throws, and it could take 5 throws. So realistically, you don't have to calculate that many. Yes, Snuffler. So that's why you get R. So that will be the last part of this is actually quite easy. But path, yeah, there is no easier way to do this. However, they're not that tricky, right? So this one, fairly intuitively, well, you want 3 successes in 3 throws. Well, let's not do anything complicated. That's just 0.25 cubed. This one here, you're going to want 2 successes in your first 3 throws. 3C2. And then we still want 3 successes, but we are going to pick up 1 fail. And Z is 5. Well, you're going to want 2 successes in your first 4 throws, so 4C2. You're still going to want your 3 successes, but now you've picked up 2 fails. All right. So now we just need to plug it all in. And I'm going to be that guy. I'm going to do it all in one go. So 0.25 cubed plus. Now 3 choose 2, I know is 3 because I was well good like that. Plus 4 choose 2 is 146 is 6. Or you can go get it yourself, right? But if you do a lot of probability, a few of these you end up knowing. I make this 0.1035. And this is what I mean, like, these formulae for the negative binomial are all well and good, but really, if you just think about what's going on in a case-by-case situation, it's just you can just vibe it out, you can figure it out. Right. Why not do 2C2? I think MG12 or 112 has answered that for me. Is because 2 choose 2 is just 1, right? 2 choose 2. Basically, because you need 2 successes in the first 2 throws, well, there's only way that's going to happen is success, success. So it's 2 choose 2, which is just 1. Okay, but yeah, it is technically there. In the same way, there's a 0.75 to the power of 0 in there as well. If you really want to apply this formula, right, if you really want to apply this formula, and in fact, this formula up here, we should probably specify, of course, that x has to be greater than or equal to r. You can't take less than r attempts to get r successes. Makes sense, right? All right. Cool. Then finally, find the expected number of throws. You can either use the formula, but think about it. Like I've been saying, if you think about the number of attempts needed for each success, well, on average, from our previous slide, it's 1 over p. So you've got a 1 in 4 success rate for your throws. So on average, it'll take you 4 successes to get the first one, 4 successes to get the second one, 4 attempts to get the first success, 4 attempts to get the second success, 4 attempts to the third one. That's it. All right, but that's 3 times 4, which is 12. So it's a fairly intuitive one, really. If we understand what's going on with the geometric, the negative binomial is fairly intuitive. All right, you can think of it as a binomial with one success strapped onto the end, which is by and large what it is. It's a binomial with a success strapped on at the end, or it's a bunch of sums of geometrics. And this is what's so cool about stats and probability, is that all these things that seem like separate and that you just get bombarded with all these formulas, it's the same thing. It's the same thought process every single time, right? What does this do for me? Well, it's combinations, right? How many ways can I arrange these things, right? Number of successes, number of fails, it's the same ideas.